Okay, this second part about hypothesis testing. We're going to aim to actually cover binomial and Poisson distributions normally. I'm going to indicate when you can actually use approximations. Effectively, you use them as you're doing the calculation of a probability for a particular test result. And the final part is actually turning around and saying, what is the actual values needed to find the critical region, and also on top of that, what is the actual significance of a test? Because when you use discrete tests, then there is often some change. The only difference with a hypothesis test is it alters one section as you're setting up, and then it actually asks you to use the end of your probability to work out exactly what is the significance. Is what's being discussed indicated to be true, or is it indicated to be false? So let's start with this first example. A doctor has a standard treatment which has a success rate of about 40% in normal conditions. So this is their normal rate. Yeah, normal rate. The normal rate is here, and that's normal. He does some research on the new treatment, and he finds that 11 out of his 20 patients, 55%. Now he thinks that this is an improvement. He's asked to test to a standard 5% significance. Now, the purpose of the test is to say, well, you've had this result, 11 out of 20 patients. The purpose of the significance is to say, would 5% of normal treatments provide that same outcome if they were done randomly by a load of other people? So what this significance is talking about is, under normal circumstances, would lots and lots of groups of 20, and it has to be of the same size, would lots and lots of groups of that, would we get 5% of them giving us 11 patients getting better? So the first start of this is to start up as normal, and we look at the equation, and we need to declare our variables. And we are talking about drug research. The treatment is improving. So I'm going to say my treatment successes is by value T. We'll look at the data and the type of information given. Well, it's a probability, and we're doing trials of 20. Notice we're doing the trials of 20 generally, and we are setting up what would the normal treatment do. Okay? So the normal treatment has a distribution which is binomial of 20 people with a probability of 40% success. This describes my null hypothesis. So this actual situation is describing the null hypothesis, and that says the null hypothesis states the probability is 40%. The alternate hypothesis, what the doctor is claiming, that he has an improvement. In this case, because he's saying an improvement, we expect the P to increase. So for P to be greater than 0.4. If it went down, it'd be making the middle, and you wouldn't go for that treatment. So he's trying to actually test and see whether or not this is good. That's the only additional line at this point. We now go on and do our normal calculations. So the test is to say, what's the probability of having 11 people succeed? And the other part people need to think about is, what other situations could be a win, so an improvement. So improvements, we're taking this 11 as being our lower threshold, but improvements could also be 12, 13, 14, all the way up to 20. So we're going to say it must be greater than or equal to the 11. this is equal by normal messing around to t is less than or equal to 10, and we can look that up in our formula tables. Using n is 20 and less than or equal to 10 for a probability of 0.4. So 0.4, come down the column, so 10 is 0.8725. So probability is 1 minus 0.8725, which is a probability of 0.1275, or 12.75%. And now we just need to make the statements confirming whether or not this hypothesis is true. So this is now where we get the additional parts again. We need to look at the 12.75 compared to the critical region. So what they are saying is the top 5%, because it's an increase, what's the probability of it being there? We said the probability was at 12.75, greater than 11. And so, according to this, we are not in the critical region, the shaded region. Because we're not in the critical region, and this is an important point, we, from this point on, do not make concrete statements. This is the only concrete statement to make. Are we in or are we not in the critical region? Other than that, we use what I call weasel words. It's ways for you to actually make a statement without being held accountable if it's slightly wrong. So if it's not in the critical region, that says there is no evidence, the evidence being part of it, to reject the null hypothesis. This then turns around and says it indicates, again, a weasel word, the doctor's treatment is not an improvement. Now, the doctor might think, okay, I'm fairly certain this was a significant outcome, and what he may do is go away and sort out having further tests. If he turned around and he just kept adding more and more people to the trials until he actually got to the result he wanted, it's called p-hacking and it's bad practice. What's reasonable in this case is for him to say, well, I suspect the biggest error, or the reason I can't get into here, is that such a small sample size has made my binomial distribution very, very flat. If I get more evidence, it should become a lot sharper, and I should get a clear indication. So he's going to turn around in this case and say, I am going to go and do another 30 trials. From those 30 trials, he finds the same proportion. He's now got another 17 successes out of 30. And it's reasonable for him to consider, let's put the lot together. I now have 28 successes from 50 trials. Now we have a look and go, what does that change in my original question? Well, now we're talking about successes in treatment, but this binomial has now changed. We're now not talking about 20 trials, we're talking 50. So he changes his test to say, I am going to do T of 50 is a distribution of binomial 50 against the original test. The original treatment only has a 40% test rate. We're still trying to find out how many or what percentage of tests, trials similar to this of the all normal one would give us 28 successes of 50 people. So we're now talking about doing thousands and thousands of trials of 50 people. What percentage would we expect to have 28 successes? So we're now saying P T50 is greater than or equal to 28. Remember, the greater than or equal to allows me to say, if we did better and we got 29, 30, 31, yeah, they're better successes. They would definitely be better at success than the 28. And this is again P minus T50 less than or equal to 27, because we're going to use our cumulative tables again. And this is 1 minus, we go to 50 table now. Remember, we've got to change the n and make sure we're reading down the 0.4 column. So there's the 0.4 column, n is 50, and we read down to find 27 there. 27 gives me 0.840, 0.9840, and this is equal to a 1.6%. So only 1.6% of original trials of 50 people would give this result. That probably will change our outcome now. So we come down, 1.6% is now in the critical region for 50 people. So 50 people, trials of 50 people. Critical region is 5%, the top 5%. We're now in the top 1%, 6%. That gives us a statement. We are in the critical region, only clear statement. Which gives us a hypothesis statement saying there is evidence to suggest we reject. We never talk about accepting the null hypothesis. We either are giving evidence to reject it or not reject it. In this case, evidence suggests we reject the whole null hypothesis. Rejecting the null hypothesis indicates that the alternative hypothesis is true. The probability has increased. Which indicates the doctor's treatment is an improvement. And again, this is an indication. Okay, so that's the end of the first one. Fairly straightforward problem. This time we're at the upper end and we've got to deal with our 5% from the top end. Unlike the previous route, it was negative. Okay, talking about Jessie in this example, is typically late 6.7 times a month to school. That's taken overall over a number of years. A new bus timetable has been created and she is late 2 times in the first month. This, Jessie thinks, is a significant, she was late 2 times in the first month. Jessie thinks that this shows that the bus has got better. We need to test it to a 5% level. So, declare the variable late in a month. The number of lates, and we've got to look at this. This statement says 6.7 times a month. That's a rate. So this is a Poisson distribution of 6.7 based upon a period of month, and I would often write a period down here if there's a possibility of being reused. That Poisson 0.67, we now need to create our insertion of the null hypothesis. Remember, the null hypothesis must be done in terms of a population parameter, and this parameter is lambda. So we say lambda for the null hypothesis, nothing has changed, it's the normal situation. Lambda is 6.7%, and the alternate hypothesis, lambda, getting better implies it is getting above or greater. We go off and do our normal calculations. The probability that a lateness, and we're saying an improvement in this case is late being 2 or getting less. So the lateness being less than or equal to 2. With a Poisson, we're going to have a quick look on the table. And if we look on the table, we look and find, no 6.7. Potentially could use a binomial normal approximation, and we would put a normal approximation at this point. We wouldn't reformulate the problem. So if we were to approximate, we'll do it here. But as we haven't been told to use an approximation, and because this actually is equivalent to something quite small, now we can do the p of L equals 0 plus the p of L equals 1 plus the p of L equals 2. This allows me to actually then turn around and do the calculation longhand, or if you have a scientific calculator, you can actually get it, a graphic calculator or one of the new super ones, to do the calculation individually. And this gives me my Poisson by, there we go. Yeah. First value, when it's 0, it is always e to the lambda, because you've got the 6.7 to the 0 over 0 factorial. That always equates to 1. Plus e to the minus 6.7, 6.7 to the 1 over 1 factorial, plus e to the minus 6.7, 6.7 squared over 2 factorial. You'll often find people factorise out the e to the minus 6.7. This part we said was always 1, plus 6.7 plus 6.7 squared over 2. If you calculate all of that, it comes out as 0.031 to 3 significant figures. That value is 3.71%. So we can now make our judgment. So this 3.7% is allowing me to actually make my comparison. 3.7%, we're looking at the top end again, looking for 5% at the top end. This 3.7 is of being greater, so it's this top end 7.1%. We're in the critical region. Being in the critical region means that we have evidence to reject the null hypothesis. And if that's the case, then we have the possibility of the alternate hypothesis, which indicates Jesse is correct, the bus timetables have got better. Okay. Difference could be if she just wants to find out, has this changed? How does that change our problem? Because we've got this situation. The lateness hasn't changed, but our hypothesis changes. So we've still got L is Poisson distribution of 6.7, and what if we test, has the bus changed? That changes my hypothesis. It begins with lambda equals 6.7, but the alternate hypothesis is lambda is not equal to 6.7. All the normal calculations go on until we get down to this section which talks about reading our 3.7 out. So if they kept to the normal bus timetables and she'd done the analysis over that time, we would still have 3.7% of buses, months having 2 latenesses in that time. That would occur 3.7%. Christian, shh. So what has changed though is where my critical region is. Because it's a 5%, that's what we're looking at as being the critical region in total. And we said it will change a total of 5%. So we have a critical region at the bottom of 2.5% and at the top of 2.5%. We calculated our value 3.71% from the top. At the top. That's now put us between the 2 levels. So we're now between the values. This says that we are not in a critical region. This gives no evidence to reject H0. And that means it indicates no changes to the bus times. Or bus lateness. Okay. There's one other little quirk that goes on with these sometimes, and they ask things like find out what the actual significance values are and what the actual significance level would be. Now it's a little difficult with this one using long calculations because we would have to play about with the numbers. If you have a new Casio calculator, the FX991, or any form of graphical calculator, you can do these values for this type of problem where the numbers are not on the table. So if I use lambda equals 6.7 and say that the number of lates is 0, 1, 2, 3, and we calculate the probabilities, I can calculate those probabilities reasonably quickly with a Poisson cumulative distribution function. 6.7. If I pause this a minute, I'll just pull up a graphic calculator to show something similar. Okay, let's pull up a graphic calculator. This is one of the Casio ones. Texas Instruments will do something similar, but you have to know your menus. Go away, Christian. So, just looking around for the statistics menu. Just make sure there's not a distribution menu at the bottom. No, it's in the distribution, in the stats. Select the option, and we're going to calculate. Oh. Christian, go quiet, please. We're looking for the distribution, so F5. We haven't got the we've got binomial, we haven't got to a Poisson yet, and here's the Poisson calculation. We want not the point, we want a cumulative because we're trying to add up the 0, 1, 2, 3, and we're doing it from values. The x is the value I want to put in, the mu is my 6.7. I don't need to store the results anywhere, so I can tell it to execute. And this tells me I have a probability of 0.001 in this area. I think it was 1, 3. 1, 2, 3. Go back, do a calculation for the 1. So we scroll up, change x to 1, do the same calculations, and this time we get 0.0097. 0.09. 0.0097, which is still under 1%. Come to 2. Go up. 2. and that gives me 0.0371, which is the value we had before. This actually means that my value is in between. Now, depending on the circumstances in the question, sometimes they may say go lower, may go higher, or generally you go to the nearest, and in this case my nearest is at 2. So the actual probability from that is 3.75. So the critical region at the lower end is at 2, and it has a probability of 3.71. And when we go to the top end, we're looking for values which might give us somewhere around 97.5. Remember, we want the top 2.5%. So bring the calculator back, go around, let's try a value 20, enter, and that's 0.999999. Effectively, that's 1.0. So this is actually telling us that out of 50 trials, out of a month, we'd expect it not to be 20 times. Bring it down quite a way then, let's go down to 15. Now this you do by scanning through a lookup table if you were doing off the tables. Here I've got these values, and that's 0.0998. Try again, a bit lower again still. Let's go to 12. That's 0.9800. So this is 2% away. Let's try 11, because we need to sandwich the two values. And that's 0.956. 0.959. So my 2.5, my 97.5% position rounds to this value, 0.98, and that is 12. So the critical regions are anything less than 2 or equal to 2, greater than or equal to 12, and the probability on this is 2%. This bottom line tells me my total probability. So notice that's 2% adrift from the whole. We've got 2% above. We have a grand total of an actual significance of 5.71%. That's if we are using the clusters value. Sometimes they will say you must be inside the critical region, and that would change this one to having a probability of 0.97%. And in that case it would actually be critical value 1, 0.9 here, 2 there. It would actually have an actual significance of 3%. That's the end with the values, apart from actually doing one with a proper normal distribution as an approximation. Like I said before, the approximation should be done only when you're starting to calculate the probabilities. You do not reformulate your hypothesis to take it into account. You do have to do all your correction factors if they're necessary to make sure it all works. Okay, good luck with the exams.